Greetings, folks. When a force does work on an object, it will either do positive work, which means it's essentially putting energy into the system, which means it's increasing the kinetic energy of the system, or attempting to. Or it will do negative work on the system, which means it will effectively be decreasing or attempting to decrease the kinetic energy of the system. In most instances, not all, but in most instances, friction pulls energy out of the system. It does negative work. So if you had a body that was moving with some velocity v, it would have some kinetic energy. And if it ran into a patch, a frictional section, friction would do work. The work would be negative. It would pull energy out of the system, and in fact could actually pull so much energy out of the system that the final kinetic energy of the body would be zero. It would actually bring the body to rest. The example that you're about to look at is using the work energy theorem to try to figure out how far an object would travel before coming to rest, given that it started off with some initial velocity and friction was acting over it. Anyway, that's what you're about to run into. So here is our system. Our mass has an initial velocity v naught. This is a frictional surface over which it's traveling. I'm assuming it's going to travel a distance d before it finally comes to rest. Just to be clear, I've tracked the body from where it was here, where it started with its initial velocity of v naught, to this point right here where its velocity is v. I've done this free body diagram, which you don't necessarily have to do, but I've done it just, again, to be clear. So I've got a normal force, I've got gravity, and I have friction pulling back on like so. And again, I've identified the distance over which it's going to travel before it comes to rest. And I'm just putting all this information out here so I'm sure that you understand what the problem is doing. So how do you approach the use of the work energy theorem? Work energy theorem actually has two parts to it. There's what's going on the right-hand side, and there's what's going on the left-hand side. Right-hand side is usually the easiest to negotiate, because all you have to do is to look to see what's happening at the beginning of the interval. At the beginning of the interval, the body was moving with velocity v naught, so it had kinetic energy 1/2 mv naught squared. At the end of the interval, it's going to have no kinetic energy. It's going to be at rest. So the right-hand side is usually the easiest to write down when you're doing the work energy theorem. And here we have the right-hand side written down. The left-hand side, on the other hand, is usually the more challenging of the two. What you're trying to do here is to identify all of the forces that are acting on the system over the interval, and you're trying to identify which of those forces are actually doing work, and once done, figuring out how much work they actually do. So the normal force here, for instance, is at right angles to the displacement. It's not making the body want to increase velocity or decrease velocity. It's doing no work. And the math bears that out. If you do the dot product, you take the magnitude of n times the magnitude of d times the cosine of the angle between the line of n and the line of d, which is 90 degrees. Cosine of 90 degrees is 0. It turns out n does no work. Same thing with mg. F, on the other hand, does work. So we have to figure out how much work it does, and that information will go right in here. So here is the dot product applied to friction. Here is the magnitude of the one vector, the force vector. Here is the magnitude of the second vector, which is the displacement vector. Here is the cosine of the angle between the two vectors. Remember, friction is in this direction, the displacement's in this direction, 180 degrees between the two. And cosine of 180 degrees is -1. So the left-hand side is simply going to end up equaling minus the frictional force times the distance over which it's applied. And that's going to end up equaling the change in the kinetic energy. And if we deal with the negative signs and then bring the frictional force down, we end up with this final relationship that identifies how far the body will travel before it comes to rest. Which is to say, we've just solved the problem. Also, for you purists out there, I just realized that I didn't put the arrow over the D here, which I should have done, and there should be a V naught here instead of just V. I should probably be shot for this because I'm not going to go back and change it. I unfortunately don't have the time, but at least you know what it should have been. In any case, using the work energy theorem is pretty simple. You identify whether there's motion at the beginning of the interval, and if there is, you write down what the kinetic energy was at that point. It'll be 1/2 m times whatever that velocity was squared. You identify whether there was any motion at the end of the interval, and if there was, you write down 1/2 the mass times whatever that velocity was, quantity squared, and you put it in that spot right there. And that's the right-hand side of the equation. You identify all the forces that are doing work over the interval, and you figure out how much work each of those forces does, and you add them all up on the left-hand side, put that equal to the change in the kinetic energy, and by the time you get done, hopefully you'll have a relationship that you can solve for whatever variable you're looking for. In short, it's easy. That's it. Have a nice evening.